Hello, I'm back. Now we're going to learn about the third and last method for L1 for proving things. So far we've seen direct derivation, essentially just use the proof rules, the 7 proof rules. We also have conditional derivation. Anytime you see conditional, that's what you use. There's one more, and it's the biggest of the bunch. It's the granddaddy of them all. It's called indirect derivation. Any proof that you're doing in this language, in L1, is going to fall into one of these. Either directly applying the rules, or you're assuming something and then showing something else, or you're doing indirect derivation. An indirect derivation is where you assume the opposite of what you try to show, and then you try to provide a contradiction. You try to demonstrate that if you assume the opposite, a contradiction ensues. Why does that work? Remember, in our language, everything is true or false. Nothing is both. So everything is either true or false, one or the other, and nothing is both. A contradiction is both. This is a contradiction. P and not P. It's raining and it's not raining. That's a contradiction. We do not allow that. That means something in our language has gone wrong. And if we find this in a proof, and it's dependent on something else, if I've assumed R, and I've gotten to P and not P, that means my assumption of R being true was wrong. I've got to take it back. And because everything is true or false in the language, if this is not true, then it's false. And so if I get a contradiction based on R, I know I got to take it back. And there's only one way to take R back, and that's to put not R. That means I can infer that not R is true. And that's essentially how it works. Now, why would you need this? I hear you crying. I think Hardegree has a good example. Let's see. Check it out. It seems like this should follow. If P is true, then Q is true. If P is true, then not Q is true. Seems like not P. I'm sorry, not P. Got that. It's like what? This is essentially the contradiction angle I was pointing to. If P is true, then Q is true. If P is true, then not Q is true. So not P. It can't be the case that P, because P entails a contradiction. If I got P, if I assumed P, then I got not Q and I got Q. That's a problem. Let's see how this works. I mean, you can derive that, right? I'll show you. Show Q into not Q. Actually, let me show if P then not Q, or Q and not Q. And what do? Conditional P, and then we have show Q and not Q. 6. We pull this down from 1 and 4. We get Q, 1 and 4. It's conditional elimination. I think we called that cell. And then from 7, we get not Q, or on line 7 that is, and we get 2 and 4, 2 and 4, cell. But Q and not Q, we can't allow that. We cannot allow that in our language. It's a contradiction, a big old no-no. That means something's gone wrong. Something's gone wrong. In our language, we're able to derive that. We show Q and not Q. Showed it here on a conditional derivation. If I've shown that on the assumption of P, what I've proven, it's like doing this conditional calculation, I got a contradiction in my language. So I can't actually allow for this. This proof doesn't actually work because we won't allow for Q and not Q. We've got to take something back. And the heart of this is taking something back. Now, here in this proof, I've not really shown how we do. I've not done like an indirect proof properly. I'm just kind of illustrating the tension. We don't allow for this. So we need some proof method to keep us on guard from deriving stuff like this and allowing for stuff like this. So we got to go some other way right? Because we want to be able to derive, like, when something on a condition of something it gives you a contradiction, we can take the opposite back. And right now, what you're looking at right now is not going to get us there. We need a method. We need a better method. And that's the indirect derivation method. So here's what I'm going to do. I'm going to show you how this bad boy works. Now, but I'm not going to use that example because I think there's a better one here. Well, I am going to use that example, but I'm going to do it differently. Okay, changing my mind halfway through. I'm just getting excited. I love indirect derivation. I love it because this is anything you can prove. Anything you can prove with indirect derivation. Anything you can prove a conditional derivation, a direct derivation, you can prove an indirect. This is the thing that allows you to prove every single thing in the language. All right. I'll put my boyish excitement aside and actually do the labor. Okay, here's what I want to do. I want to show not P. Right? That's the sort of insight that we were having, right? If I have P then Q, and I have if P then not Q, it should follow that not P, right? I think I wanna demonstrate that. I wanna show that. Now how do I prove it? Alright, so check it. Think about your basic rules. You don't have any basic rules that are going to allow you to pull out anything here. For conditional elimination, you need at least two lines. One of them is the first part of the conditional, and then you need the conditional themselves. You don't have a first part of the conditional. You don't have not P. That's something you need to prove. You don't have P anywhere. So your rules aren't going to help you. You also don't have a conditional in the show line. There's no conditional here, so you can't apply conditional derivation. This is where indirect derivation comes in. For an indirect derivation, you take the first thing, you take the thing you're trying to prove, you assume the opposite, and now you see what happens. If P is true, then Q is true. And that was from line 4 and line 1, conditional elimination. Now, similarly, from line 2 and 4, oops, no, I'm sorry, I wrote that too high. CL, and then from 2 and 4, CL, you got not Q, dun dun dun. Line 7, you have Q and not Q. Can you see that? Now here's something I like to put in this because, as I told you, I'm a bit of a drama nerd. No, not nerd. I just love drama. Okay, 5, 6, bang. Bang, you got a contradiction. Something's gone wrong. You can't allow for that. So what do? We box that up. We boxed it up. We shielded away from our proof. We boxed it up. We've shown this thing. We're going to mark that off. An indirect derivation. How does that work? We wanted to show not P. We showed that if we assume the opposite, P, we get a contradiction. No contradictions are allowed in our language. So we know we did something wrong. We only made one choice. We assumed P. P is true or P is not true, one or the other. So if P gets us a contradiction, P can't be true. That means not P has to be true. So we've demonstrated that not P is true using indirect derivation. So these premises get us there. Let's try some more. Give you a couple more examples, give you the schema. I'm going to give you some more examples, just a couple. And then we're going to move on back to that insight, and I'm going to leave you back or out to your day. So we've discussed, this is what I want to show. We've discussed the equivalence between P or Q. Now, if you want to check, you can make truth tables for these two, and they're going to come out to have the same truth values. But we want to be able to derive one from the other. and the other from the one, right? That's how we show they're equivalent in our language. And so if not P, then Q. I want to show that's equivalent to P or Q. Now, you're not going to be able to use proof rules here, so you've got to do something else. How are we going to do that? I'm going to negate P or Q for indirect derivation, right? Right, and then we're going to try to find contradiction. Now, we can technically assume whatever we want. That's some of the beauty of this. We can technically assume whatever we want, whenever we want. Now, you can't always break out of your assumptions. You have to find, usually you have to discharge, we say, your assumptions with a conditional, or apply indirect method and find a contradiction, and then you can take back what you assumed. So it's technically okay to just plug in an assumption wherever you want. Now, we can do that here. Let's say I want to show not P, because I want to get Q so that I can infer if Q then P, or if P then Q, or P or Q. So I might just assume, just as an assumption, for maybe an indirect derivation, just like I did up here. I'm trying to assume something's false, but now I want to just kind of effectively want to prove P is true based on these premises, but I want to try to get there through an indirect derivation. Now, if I'm doing that indirect derivation, of course the next thing I have to do is put a P down, right? That's my assumption. I want to show this, so I assume this. I want to show not P, so I assume that. And now, what can I do? Well, P or Q for sure follows, and that's from line, what is it? That is like from line 5. Disjunction introduction. Now I've got that so far. Now that is the opposite of line 3. So I've got a contradiction. I'm just going to put a bang here, right in the line, right there. It's a bang between 6 and 3. So 3 and 6, bang. Now what I've effectively done is that on the condition of P, I showed a contradiction. That means not P is true. Now if not P is true, keep going. Not P is true, then Q is true, right? Because I've got line 4, not P, 1 and 4, and that is from conditional elimination. Yeah. Now with Q, I can just directly infer, I'm going to have to do it over here, P or Q. Now P or Q, that's from line 8, disjunction introduction, and that comes, I'm going to box up, box, all the way up here. Now what I did, again, I assumed for indirect derivation, I got not P. And now I've gotten P or Q, and that is a contradiction with here. Right? There's a conflict, so I can write, I should actually, from being correct, and I want to be correct, so you learn this, I'm going to go boom, a bang, and that's because 9 and 3, bang, got my contradiction, mark that off because I can't allow for them, can't allow for contradictions, and so if I get, on this assumption, that is to say, if I assume not P or Q is true, then I get a contradiction, so I'm allowed to infer P or Q. Now, let's see, got some more cool ones. Got like a whole test bank here. It's a lot of fun. All right, I'm gonna try one more. I'm gonna show you this. Hopefully the lesson's getting through. Indirect derivation, P or Q, then P and Q. Now, what I'm going to do is I'm going to show P and Q, or not P and not Q. Now, how am I supposed to do this? I want to show that there's an equivalence between these. I want to show there's equivalence between these, but I actually don't know how to break this stuff apart, right? To get to this place, I actually need to show something else. I need to show how I can like move negations into and out of connections like this. So this proof is actually a little too sophisticated for us right now because we need to prove some other things to build up to this. So what I need to do is I need to figure out a way to derive something like, I don't know, from this to show something like, just off the top of my head, P or Q. And so I actually need to back up and do that instead. This will be illustrative because, well, we've actually seen some of this before. We called it De Morgan's Law. We haven't actually shown you how to prove it yet. So now we're going to demonstrate this is true. And when we demonstrate this is true, we can actually use an abbreviation for it in our reasoning. So in our proofs, that way we never have to do it again. And that's key, because we want to save ourselves some time. So I can do this by an indirect strategy. So P or Q. I'm assuming it to see if I can get a contradiction, right? Now, what would be a contradiction here? Now, all I have, things like not P. I have things like not Q. I can derive that for sure. That doesn't get me any kind of contradiction here, does it? Let's see. I do have this, well, just so I'm clear, I have conjunction elimination, conjunction elimination. I've got P. Now, I want to infer disjunction elimination. I can get Q, right? That's 3 and 4. Disjunction elimination. Now I've got my contradiction. Bang. 5, 6, bang. Now, what is that showing me? On the assumption of P or Q, given this, I've gotten a contradiction, so it is the case that not P or Q. Again, as I said, this is a rule that we can cite, we can use. This is called De Morgan's. One of the directions of De Morgan's rule or law, it works just like this. Anytime you have phi and chi, you can pull out the phi, or the negation, as long as you change the connective. And there are actually 4 directions. You can move the negations back and forth into and out of the parentheses. Now, going back to what we started with, I had P or Q, or if P or Q, P and then P and Q. And I was saying, show P and Q, or not P and not Q. And I had gone down that detour because I didn't really know how to do anything like break this stuff apart. I didn't know how to break out the negations. Wasn't like trying to prove a conditional. None of my proof rules worked. I could negate all of this for sure, but like for indirect derivation. But look what happens when I try to do that, right? P and Q, or not P and not Q. Just using brackets to help arrange this, but like you see, which way am I supposed? Okay, you see now I've got like a negation on around all this complicated mess, and up until a minute ago I didn't really know how to deal with that, right? Now I've got some insight. I do know that it's possible to move negations through as long as I change the connectives. Now, I was, if you're paying attention, showing how you go from something like that to something like this, right? Where I've changed the connective from a conjunction to a disjunction. But here on the outside, I've got a disjunction. This rule doesn't apply. It would apply here. I could derive from here, not P or Q. That would follow. But I can't really connect this to the disjunction. I don't have a rule yet that allows me to do that. Remember what I said, there are 4 directions of De Morgan's. So what I actually need is to be able to do something like this. I need to be able to go from a negated disjunction to conjuncts that are negated. Which is to say, I'm going to back up one more time. I got to try that again. I need to prove that from not P or Q, it follows not P and not Q. How am I supposed to do this? Well, check it out. If I assume the opposite, not P and not Q, and you remember, I just showed you, if you have a conjunction and a negation outside, we know how, just De Morgan's rule, we just showed it, we know how you can push in the negation, right? It was just this. We proved this a second ago. Sorry. You have, what was it? Not phi, not psi. And we know how to go from there to not phi or psi. Right? And this was De Morgan's. We're going to put dm. We know how to deal with that. So let's do it. Let's apply it so I can push the negations in. So now I've got not P or not Q. That's line 3, De Morgan's law. I know how to get rid of double negations, for sure. I'm just going to drop them off, P or Q. Now I'm going to call that for negation elimination. Not a big deal. Drop them off, add them on, drop them off. Okay, now what do I have? I have a contradiction. I have on line 6 a conflict between 5 and 1. That tells me that I made the wrong assumption. That I can indeed move from this to this, which is to say, if I were to do that more schematically, just as kind of a guide, I can go from not phi or psi to not phi and not psi. And I will also call this De Morgan's. Just pushing and pulling negations too. So I've proven these. Now let me go back one more time. P or Q. If P or Q, then P and Q. I need to show that P and Q, or not P and not Q. I'll move these. I'm going to assume, for the sake of trying to find a contradiction, the negation of the thing I'm trying to show. And now I'm going to use De Morgan's to distribute through. Now with De Morgan's distributing through, what I get is not P and Q and not P and not Q. Remember, what am I trying to show? I'm trying to show a contradiction arises between this and whatever I can derive here. You see something? Anything jumping out at ya? I know this much. I can derive not P and Q And I can do this. Oh, I should have cited this. This is 4. This is 3 De Morgan's. And this is 4 conjunction elimination. I can also derive, that should be parentheses. I can also derive not P and not Q. And that is also from 4 conjunction elimination. Now I know how to move this negation through, and I'm just going to skip some steps because I know this is P or Q. So I move the negations through. I'll get not P or not Q. I'll just do a little double negation elimination step, and ultimately I'm going to get P or Q. I'm just going to cite that as 6 De Morgan's. Now what do I have? I have P or Q. On line 8, I know that if I combine P or Q with line 1, then I can get P and Q. So far so good. So that's 1 and 7 conditional elimination. And now I've gotten P and Q. Now why is that important? Well, because line 8 is in conflict with line 5. Line 8 and 5, bang. 8 and 5 together are a contradiction. That means I've shown that on the assumption of P or if P or Q, then P and Q, then it follows that P and Q or not P and not Q. Now I had to go through a couple of extra steps. I proved some De Morgan's laws to get there, but now we have those in our repertoire. Now we can use them, and we did it by indirect derivation. We only have 2 of them. There are 4 directions in total. But you have them nonetheless. Now, altogether, I'll just write them. You have De Morgan's, the different versions of De Morgan's. You have 1. You have this. You have. You can go the other direction. You also have this direction. You also have this last one. Now we've proved 2 of these. You can prove the rest, and that is enough for me. I will see you next time. Please practice. There again, there are plenty of examples in the textbook. You should go rogue on it because there are plenty of solutions as well. Hardiger is a fantastic example. Just remember 3 methods. That's all you need: direct derivation, conditional derivation, indirect derivation, and you'll be a master at this, no question. Take care. I'm gonna come back with a 10. Peace.